Okay, so another kind of problem that you run into are solubility problems involving buffers, because as we pointed out, carbonates, which are conjugate bases of weak acids, and things like uh, sulfide or hydroxide, these are all things that are generally insoluble, and their concentrations are all affected by pH. And so you oftentimes will see a buffer in a problem. So I'm going to go over this problem and show you how you deal with the buffer. But really it's two separate problems, and we assume that the buffer sets the hydroxide ion concentration, and that will be the equilibrium concentration that we deal with for calculating how much of a particular metal ion is soluble in solution. So let's go through this problem. It says an acetate buffer contains, and it's acetic acid and its conjugate base sodium acetate. If 0.25 grams of magnesium nitrate is added to 50 mils of the buffer solution, sorry, there's a word missing, will magnesium hydroxide precipitate. Okay, so we have the buffer and we're adding magnesium to it, and we're asking whether or not a magnesium hydroxide precipitates. Okay, so first thing to do is look up your KSPs, and then also look up your acid ionization constants, and also write the reactions out that are important. So let's deal with the buffer first, right? This is an acetate buffer. Ka is 1.76 times 10 to the minus fifth, and you'll use a Henderson-Hasselbalch for this. As long as these are within a factor of 10 of each other, the Henderson-Hasselbalch equation works just fine. So we're going to say pH is equal to pKa plus the log of the base, right, over the acid. So I'm going to call it A minus over HA. So negative log of 1.76 times 10 to the minus 5 is 4.794 plus the log of, and then again, this is the acetate, so this will be on top, 0.65 and 0.25. Okay, so that ends up being 5.169, and that's the last sig fig 46, something like that. So that means we need, the reason we're calculating the pH is we need the OH concentration. So POH, that's going to be 14 minus pH, right? So that'll be 8.305. And then the concentration of hydroxide is 10 to the minus POH. So that ends up being 1.477 times 10 to the minus 9 molar. Okay, so that's all the information that you need out of the buffer. The next part is to use that number and to calculate Q. Okay, so again, asking whether or not, right, magnesium hydroxide will precipitate. So we need to calculate Q, which of course means we need to know what Q looks like. And Q is going to be the magnesium concentration times the hydroxide ion concentration, and we get that from the equation, the solubility product expression equation. And then we have the OH concentration. Again, that's this number here, the 1.77 times 10 to the minus 9 that we did here. Yeah, 1.477 times 10 to the minus 9. And then we just need to know what the magnesium concentration is, right? So look at what our data was that we were given before. We're adding 0.25 grams to 50 milliliters. And so what we're going to need to do is figure out how many moles of magnesium nitrate we just added. So to get this, I'm going to have to convert 0.25 grams of MgNO32 into moles. And then I need to get it into molarity units, and I'll use the volume for that. And you're going to have to make an assumption when you do this. You're going to have to make the assumption that the volume doesn't change when you add the solid to it. Okay, so you're going to assume that the volume you started with hasn't changed much, and it's probably true, but I don't know for sure. So 0.25 grams is added to 50 milliliters. So my volume here is 50 milliliters. So let's go ahead and do our calculation. We know that we can calculate this molar mass, and I'll just be honest with you, use an app. It's 148.3 grams per mole. So 0.25 grams of magnesium nitrate times, and then 148.3 grams for every 1 mole. And then, that'll give me my moles. That ends up being 1.688 times 10 to the minus third moles. And then I need to calculate the molarity. Now, it's not in millimoles, unfortunately, so I could either convert the moles into millimoles and divide by the milliliters, or I could convert the liters into the milliliters into liters and divide by liters. And it turns out for this one, that's a milli. That's actually easier. So I'm going to divide it by 50 milliliters. I know I went not the way you were hoping, I'm sure, but that's okay. This will cancel. Well, not that won't cancel. This will cancel, and I'll have moles per liter. That ends up being 0.0337. All right, so now what I can do is I can go ahead and finish calculating the Q value. I have a 0.0337 here, and I have a 1.477 times 10 to the minus 9 here, and this is squared. And I end up getting Q being equal to 3.67 times 10 to the minus 21. Okay? Now, what is that telling me? It tells me nothing unless I know what K is, so that's why we looked it up earlier, right? And KSP is 2.06 times 10 to the minus 13. So going back to here, what we know is that Q, right, is actually much smaller than KSP. So, in other words, what that means, it means that you don't get more dissolving, right, because you didn't put any solid magnesium hydroxide in there, but all of the solids should remain dissolved. Or the other way you could say it is none of the ions will precipitate because Q is less than K.